If enough heat is transferred into or out of an object, then a phase change might result. For this reason, it's interesting to look at the characteristics of the common phases of matter. So matter can exist in one of several different states, including gas, liquid, or solid state. The amount of energy that's in a sample of matter determines its state. In a gas, the molecules or atoms that make up the sample are in rapid random motion. That is, they have relatively high energy. There's a lot of space between the particles, which results in gases having low density. And interestingly, the gaseous state is the only state of matter where a sample of matter will completely fill its container. Put a gas in a bigger container and it will spread out to fill the new space available to it. This is quite unique. Other states of matter don't do this. In a liquid, the molecules or atoms that make up the sample of matter are in close contact, but they're able to move. So they have less energy than gases. There is a little bit of space between the particles, but not very much. So they have high density in comparison to gases. Liquids have a fixed volume, but they do have a variable shape, and the shape of a liquid is simply the shape of the container that you put it in. The fact that they have fixed volume is why we are able to use things like graduated cylinders and measuring cups to measure out the amount of a liquid, because when we pour it to another container, the volume won't change. In a solid, the molecules are very close to one another, and they are not moving very much at all. Thus, we say that solids must have lower energy than liquids. Because there is almost no space between the particles that make up a solid, solids have high density compared to gases and liquids. Solids have fixed volumes just like liquids. The volume does not change with the size of the container. However, solids have their own unique shape that is not dependent on the shape of the container that you put the solid into. Matter can move between the three common states by either removing or adding heat. For example, if I take a solid and I add some heat, then it will melt and become a liquid. If I continue to add heat, then it will evaporate and become a gas. We say that melting and evaporation are endothermic because to make those things happen, you have to add heat. We'll talk more about the term endothermic a little later on. If I have a gas and I remove heat from it, then it will condense and become a liquid. If I continue removing heat, it will eventually freeze and become a solid. So we say that going from a gas to a liquid or from a liquid to a solid are exothermic processes, as we need to remove heat to make those things happen. And again, we'll talk about that term exothermic later on. The important thing to note at this point is that if a process is exothermic in one direction, then it is endothermic in the other. So going from a gas to a liquid is exothermic, but going from a liquid to a gas is endothermic. So we should point out a little bit of the anatomy of these words. Exo, obviously meaning outside or exit, and then thermic, meaning heat. So it means that heat is being transferred to the outside or heat is exiting the system. Endo means inside, or some people say it means enter. And then again, thermic meaning heat. So this means when we say that something is endothermic, that heat is entering or going into our system. You should know the names for the common changes of state. So a solid becoming a liquid, we call that melting, or sometimes fusion. A liquid becoming a gas, we call that vaporization, or sometimes people will call it boiling. When a liquid becomes a solid, I only know of one name for this, we call it freezing. When a gas becomes a liquid, we call it condensation. And when a solid becomes a gas without going through the liquid state, we call it sublimation. And the only one that I can think of that isn't in this table is when a gas becomes a solid without going through the liquid. They call that one deposition. You should know these names. If I take a sample of ice out of the freezer, it'll be about minus 18 degrees Celsius, depending on how cold you have your freezer set. If I start adding heat to that ice, it'll warm up. And it'll warm up kind of, the more heat I add, the more its temperature will rise. Until I get to the melting point of ice. At that point, the solid will start turning into the liquid, but the temperature will stay constant. Once my sample has been 100% melted, as I add heat, the temperature will rise again. That is, until we get to the boiling point of water. At that point, as I add heat, instead of the temperature rising, what happens is our sample boils or evaporates. Once all of my sample has been turned into gas, if I continue adding heat, the temperature will start rising again. So, a couple of things here to take note of. As we add heat to a sample of matter, it will change from solid to liquid to gas. But what's interesting is that phase changes always occur at constant temperature. As we add heat, we don't change the temperature, we just change the phase. The heat of fusion, which we indicate with this symbol here, is the amount of heat per gram, or sometimes the amount of heat per mole, required to melt a substance. So it's a measure of the energy that is required to take a sample from being in the solid state to 100% being in the liquid state. So the heat needed to melt a particular sample can be calculated using these two expressions, and the expression that you choose depends upon whether the heat of fusion is given to you in units of energy per gram or whether it's given to you in units of energy per mole. If the heat of fusion is given to you with any units of energy per gram, to calculate the heat required to melt our sample, we just take the mass in grams and we multiply that by our heat of fusion. If the heat of fusion has units of energy per mole, then to calculate the amount of heat required to melt a particular object, we're going to take the number of moles of matter that are in that object and multiply that by the heat of fusion. The heat of vaporization has this symbol, and what that is the amount of heat per gram, or sometimes per mole, required to evaporate a substance. And it should be pointed out that this is also the amount of heat that would be released when a substance condenses. So the heat needed to evaporate or condense a sample can be calculated using these two expressions, and the expression that we use depends upon the units that are given for the enthalpy, the heat of vaporization. Getting a little ahead of myself there. If the heat of vaporization has units of energy per gram, to calculate the heat required to evaporate an object, we're going to take the mass of that object in grams and multiply it by its heat of vaporization. If the heat of vaporization has units of energy per mole, we're going to take the number of moles in our object and multiply it by the heat of vaporization. And I should point out here that N is often used to indicate the amount of something in moles. So N represents the number of moles, and a lowercase m is used normally to indicate the mass in grams of a substance. So let's look at an example problem from the book. It says, how much heat is necessary to melt 55.8 grams of ice? So mass equals 55.8 grams. And then it says the heat of fusion, I'm going to use its symbol there, is equal to 79.9 calories per gram. So to get the heat is going to be quite simple. We just have to take the mass and multiply it by the heat of fusion. And hopefully you can see by how the units work out that this is going to return us units of calories. There we go, grams cancels out and leaves us with calories. Now we'll have a look at this and think about significant figures. This number here has 3 sig figs. This number here didn't get used. And this number here has 3 sig figs. So once I've performed this calculation, I'm going to round my answer to 3 significant figures. So 55.8 times 79.7. And then that comes out to be 4,450 calories. Here is another one. It says how much heat, so we're trying to solve for heat, is necessary to vaporize 685 grams of water. So our mass is 685 grams at 100 degrees Celsius. And then it says the heat of vaporization equals 540 calories per gram. So this should be relatively easy. Q equals M delta H vape, and we can see that Q is 685 grams times 540 calories per gram. So to see what we get, we'll put that into the calculator. 685 times 540, and we'd like to have this number here is 3 significant figures. This one here is 2 significant figures because the trailing 0 doesn't count. So that means that this is going to be 3.7 times 10 to the 5 calories. And I used scientific notation there because I didn't want to write out all of those zeros at the end. Okay, so that concludes the section on phase changes, and I hope you found it helpful.